two systems in two different effective temperatures brought into diffusive contact, what would govern their thermalization? So this is the question. This is the first system, and we're going to use holographic optical tweezers. I don't think I need to introduce tweezers here in the audience, but we have the intensity gradient force that is used to trap the particle actually depends on the refractive index, or the ratio of refractive index between the particle and the medium. And so if you take a particle that has a refractive index lower than the medium, you're in repulsion mode, and you actually get 40 of them. So we design the appropriate hologram, which is turned into this is a phase hologram. It's turned into an intensity hologram, which gives you these spots here. And we can change them as we go. So what we're going to do is we're going to project a set of random traps and then switch them to the trap and then decays. So let's say I projected a trap here. It applied a force on my colloid, and the colloid, it's a repulsion trap, so the colloid went away. Then I switch my pattern. The colloid now has to go to another way because it's pushed away by the traps. And then if I look at a movie of a colloidal particle in such traps, you can see that once in a while it jerks. This is the fluctuations that I'm imposing on this. So I'm making random forces on the colloid, mimicking temperature to some extent. And the question is me mimicking temperature good enough? Okay, so then if I work in attraction mode, then you can see that the particles are drawn to the trap and are local until I switch the trap position again. So as I increase the switching frequency, my motion looks more and more random. And with the repulsion mode, it's a bit different, the effect. In repulsion mode, particles are confined to some area where traps are far away. If I'm in slow switching modes, but as I increase the frequency of my switching, I'm going more and more into something that looks very normally diffusing. And you can think of this as two types of games. So we're going to do the pinball. Okay, so now let's plot the PDFs of the particles at different time steps, and they look Gaussian, and the diffusion looks normal. So it all really gives a feeling like equilibrium. We wanted to test if our traps affect the resistance, the dissipation, the drag force. So if you can imagine that if I'm trying to move a particle and there are these forces acting, they might affect the drag. So for attraction and very slow frequencies, we can actually see when you pass the bead through the trap array, you can see a reduction in velocity, and really the drag changes. For repulsion, there is a minor effect in the low frequencies, and then it disappears. So you can assume that for most of our experiments, the drag was not affected. And so then we use the Einstein relation to measure the effective temperature. So there's simulation and there's experiment. They're different. In experiment, we have hydrodynamic interactions, which are suppressed by the vicinity of a single wall. In simulations, it's just a Brownian motion. We don't simulate the hydrodynamics. And then you divide these two, and you get the effective temperature. And now you can notice something interesting. The effective temperature has a maximum, which means that I can drive the system with two different frequencies, say around 1 and 5 here. And they will be in the same effective temperature, but the microscopic behavior would be different. And now, if I put this one next to each other, will there be flow of particles from one side to the other or not? Is it a real temperature, or does it behave like a real temperature or not? We simulated, as I said, the Brownian dynamics of the system. You can see that if you do, this is different frequencies. So at high frequency, the system really behaves like almost constant force every time I switch the traps, and this is very much like equilibrium, whereas if I switch the traps very slow, you can really see the particle relaxing to the area of least potential around it, and so this is intuitively far from equilibrium. Or maybe more, these types of forces are less like thermal noise. We can define from these simulations something that would behave like the the effective temperature or the effective diffusion coefficient, because you have this added term here that looks like the amplitude of the force squared multiplied by the persistent time. So the persistent time does play indeed an important role here. And then if you plot this effective diffusion that we calculated versus the diffusion that we measured from the diffusion coefficient, you see that for high frequencies, what you see here in the orange, they agree. And this goes back to other experiments that really showed that the fluctuation dissipation relation also holds only if your forcing, your stochastic forcing is fast enough. How fast? Faster than the relaxation in the system, the thermal relaxation in the system. So this is, so this is something we see as well. So we're going to focus on this region where the fluctuation dissipation relation holds, which is high frequencies. And so now we're going to make a diffusive contact and ask the question, if the temperatures are different, do particles go from hot to cold? If we change the frequency in both sides but have the same temperature, is there a particle current or isn't there? And so this is the experiment. You have a hot system on the top, you have a cold system on the bottom. Notice that to do hot and cold, what we do is we project a different frequency of trap formations in the top and in the bottom. To make it hot, we project very fast, the frequency is higher. To make it colder, the frequency is lower, or we just tune it according to the calibration between frequency and temperature. And you can see that with time, the density increases in the cold area. So it's not that all the particles flow to the cold area, there is just a difference of density, and this is expected also in equilibrium. So what happens if you have the same, if you have the same frequencies as what you see here in blue, and you look at the probability to be in the hot side, then nothing happens, and you wouldn't expect anything to happen because this is the same frequency on both sides. This is a control. But if you project different frequencies, but the same effective temperature, you still get that nothing flows. So this is very encouraging. This means that really you could use the effective temperature to predict particle flow in a diffusive contact. You could take it, of course, to increase the temperature in one side, and then you see particles flow away from the hot area to the cold area. And these experiments were very, very encouraging, and we decided to do simulations and test the whole range. You know, in experiments, it's
in the previous slide, the frequency was high frequency? I mean, the one where you had the two different microscopic...
one of them was higher than the other.
Okay.
Okay, so different frequencies, different microscopic behaviors, but the same effective temperature according to the calibration curve.
But both...
Still in your region of high frequency?
Yeah, that's what I mean.
Both of them are in the region of high frequency.
Yeah.
Yes. And this, I'm leading up to this exactly, so thank you for the questions, because when we sort of extended the range and went also to weaker frequencies and so on and so forth, everything broke. So we could see things, different things, and we had to put everything into the order, and then only then we went actually back and saw that only the high frequency works. So you have to have a high enough frequency to define the fluctuation dissipation relation before you can go ahead. Right, so that's only one step of the case, but I want to be able to predict everything. So do the densities that I get in the end, the steady, so you can see here there are steady state densities. Can I predict them from the chemical potential of the gas, of the colloidal gas? So what I'm going to do is I'm going to use the effective temperature that I measured and the densities that I have, and then I can plug it into this equation and get the chemical potential. So the densities I measure, the effective temperature I measure through the diffusion coefficient, and then I get the chemical potential, which is something that I did not measure. And so, of course, in this set of simulation and experiments where the density was a constant, everything behaves like, it depends only on the temperature. When I let two systems come together and they are different in density and different, they always start in the same density, but they're ending up in different densities, and they have different frequencies and different temperatures, and everything is different. When I see what is the effective temperature in both sides in my different experiments, so this is something that we plugged in, and this is my chemical potential in the different systems, and it looks like. So in purple you see the left one, in orange you see the right one. They should coincide if they agree in equilibrium. So clearly the temperature itself is not equal when they cease to relax, and the chemical potential is not equal, which are the two things that we require in thermal equilibrium. So what's going on? So we know that in equilibrium we require the entropy to be maximized according to the internal energy in order to get an equilibration of temperatures. But actually in our case, things are different. When particles flow from right to left or from left to right, they don't carry heat with them because the heat is generated by the tweezers on the side. So actually there is no maximization of internal energy because of heat flow, because there is no heat flow. So if you go back to the second part where you maximize entropy according to particle number, actually the condition is beta 1 mu 1 equal beta 2 mu 2. And maybe this is what should be holding, because the temperatures would never equilibrate. We are forcing them to be different on the two sides. So we checked this, and you see here the minimum density, the minimum frequency. So we have two systems, and we needed the minimal frequency of the two sides would be high enough. So if the minimum frequency is high enough, then we get complete agreement between the two sides of the experiment with beta mu 1 equals beta mu 2. This doesn't happen at lower frequencies. And you can also add our experiments here on the plot, and you can see that in the higher frequency this holds, in the lower frequency experiments that we did it doesn't hold. And so we can come to a conclusion that defining an effective temperature for systems that are driven or out of equilibrium really can be extended, at least in this case, also for a diffusive contact, provided that the system is dilute and that the fluctuation dissipation relation hold. So this was a happy occasion. I have to say, we still don't have an explanation of what happens at low frequencies, and it's not clear that you can treat the tweezers' forces as stochastic thermal forces. Maybe in that region you should think of them as just an external force. So I don't know, open question. The second system I wanted to tell you about is this a driven system.
Sorry, Anna, so let me,
Yeah.
before you move on. So since you're trying to see whether this acts like temperature, can you look at the fluctuation spectrum of your forcing and see if it's white noise or not?
It's not. It's definitely not.
So it is colored noise.
It's color noise, because what I'm doing is I'm controlling the frequency of switching of the noise. So underlying everything is the frequency I put in. This is not white noise.
But if it's colored noise, then why is it temperature?
It's not temperature. So if I go back to the original question, and also in this system, the other system, the noise is not going to be white. So I'm asking what is required of the noise, and it turns out that it doesn't have to be white.
I see.
Okay, it
It's
doesn't.
colored, but does not anything happen to that spectrum as you go to these higher frequencies? Like, does it become more like white?
It becomes more like white noise in one way, which is that the time scale between kicks is very fast, right? So that means that the system cannot relax.
Yeah.
But if you, in a complete different set of experiments that I'm doing, if I had a potential there, you could ask what is the coupling, or how many degrees of systems, or if the molecules were, you could ask, what am I exciting? How many degrees of freedom am I exciting, and does that depend on the color? There you expect things, interesting things. But here, the system is flat, there is no potential energy, the interactions, it's a dilute system, no interactions. weak interactions, hydrodynamic interactions. They are not dependent on the frequency mode. You're not exciting any frequency modes special. So in these cases, it doesn't matter if it's colored, or I can take it far enough even if it's not colored, if it is colored. Okay, so this work of this styrofoam ball, here we also have colored noise. So the collisions they can be frequent or they can be sparse, but they are definitely not white noise. Okay? And this work, Dima Boryskovsky, whom is a PhD student that is finishing in my lab, and I highly recommend, and Benjamin Lindner, my collaborator in Berlin, have a lot of contributions here. Okay, so this is actually a ball. And here it's an old experiment where we have this ball and the many particles, which you can see some have fallen aside and so on and so forth. But the idea is that we have a system that is very much like a particle in an optical tweezers. You can watch the motion of the tweezer. You can watch the motion of a styrofoam ball in a bowl. Nothing happens unless I blow wind, and then it moves. And you can watch the motion of the ball with the hex bugs inside, with and without wind. And so my fluctuation dissipation experiment will be to turn on this wind, push the styrofoam ball upwards, and then close the wind and have the particle relax. So this is just, the wind comes from this direction. This is my Bristol bots. They are all here. So we are going to map everything onto the x direction and disregard the other directions. This is a trajectory. We're going to turn on and off the fan and record the trajectory of the particle. And then we're going to cut equal pieces where the fan was on and off and average over all of them. And we get here the average plot. And you can see that there is a response region. And we're going to compare the response here in this region to autocorrelations in the steady state region here. So in blue, you see the correlation, autocorrelation of the x variable, and the response of the x variable to this, to closing down the wind. And the fluctuation dissipation, of course, the regular fluctuation dissipation relation doesn't hold, but if you generalize it and define an effective temperature, then it does hold. And not only that it holds, this effective temperature is related to the variance of the trap, which is exactly what you would have so you get something that is very similar to what you would have in equilibrium. So you don't have to guess this constant, you just have to know the stiffness of your trap, and you can extract that effective temperature. Now what we can do is we can change the number of bots in this experiment. And it will give you an idea that the number of collisions or the frequency of collisions changes as we increase the number of bots. But also in this system, the total energy you inject into the system changes when you increase the number of bots, because your system's energy is basically the number of batteries you have in there. And you can also see that when we get to 15 bots, the area where the particle is kind of dense already, and going more than 17 is, in this specific system, hard. The dynamics of the styrofoam ball are underdamped, as you can see from the correlation function. And as you increase the number of bots, they become more and more damped, reaching to critically damped dynamics. They never reach the underdamped dynamics. And the probability distribution of finding the particle at high numbers of bots, it's Gaussian. And you can extract from there the effective temperature. But also, when there are a few bots, it's completely not Gaussian, and still the idea of the effective temperature, the autocorrelation at 0 time, still works. So we don't need them to be, the color can be the noise can be colored, and the PDF can be non-Gaussian, and we are still fine with this. And now, as we look at the effect of changing the number of bots, and between 4 to 17, the fluctuation dissipation relation holds for all of them. And this is the non-Gaussian parameter. You can see how the system decays into Gaussianity as the damping increases, and the effective temperature increases. So this makes sense. Maybe we would have thought it would increase faster, but this is where it goes. And now we want to look at a different way to look at the fluctuation dissipation relation is to look at the response versus the correlation, and you can see they all fall on a straight line as you increase the number of bots, and you can extract the temperature from the slope of this line, except for when you have 2 or 3 particles. Then this doesn't hold. And you can ask, why doesn't it hold? And what we did is with this no bots experiment, we looked at the response of the system to turning off the air. And when you look at this, you get a response, and it means that there is some decay. You see it's not oscillating like a harmonic oscillator. So there is damping in the system, and this means that this particle actually experiences damping from more than one source. One source is the collision, and the other source is the ball, or the air, or whatever is going on there. And so if you go back to the idea of having many sources of fluctuations and many sources of dissipation, how can the fluctuation dissipation relation hold in that case? It needs to hold somehow, even though you have everything. And so the claim that we are doing here is that what is important is the dominant process. If the dominant process of fluctuation and dissipation is the same process, then you expect fluctuation dissipation to hold. And so in this case, there is no fluctuation, there is only dissipation. In this case, where you have only 3 particles, the response of the system in red almost follows the cyan-colored response, which is with no bots. So it means that the dominant process of dissipation here is just air and the ball and everything, and not the collisions. And then the fluctuation dissipation doesn't hold for 3 bots. This is what you're seeing here. But if you go high to 15 bots, you see the response sitting with the autocorrelation and completely not with the 0 bot system, because here the dominant process of dissipation that arrests the relaxation of the ball to the center of the ball is the collision. And this is the case in most of the system, and this is how we get fluctuation dissipation in this system. So the conclusion of this system is that the Bristol bot systems obey the fluctuation dissipation relation. We don't need Boltzmann statistics or overdamped conditions in order to get this. But we have looked at a dilute system again with a single dominant channel in both fluctuation and dissipation. So you can ask, how far can you go? So I've shown you again that there are conditions where the fluctuation dissipation relation holds. Does this system do something else which is thermodynamics-like? So for instance, will it obey all kinds of temperatures? We know that out of equilibrium, the effective temperatures, each one is a different one. So maybe in this system, they all coincide. So this is what we try to check, and so we measure the mean kinetic energy of the styrofoam ball, and we measure the potential energy, and if equipartition holds, then they should be equal, and you can see that they're not equal. And this is the naive raw data that you get, but then you realize that the fact that you have bots in the system modifies the potential because physically they are there and they're modifying the shape of the potential. And also, so you could think of this as potential change or mass change, but if you renormalize, according to the autocorrelation, you extract from that the K over M and correct, then you get equipartition to some, for a small number of bots, and only when the number of bots really increases, you deviate. So we have equipartition. Now you can say, if this is so strong, what happens if I put bots which are faster? What happens if I put a ball which is heavier? This still should hold, and this is what you're seeing here. For the faster bots, you have a regime which holds, and for the heavier ball, this holds nicely. I should say that if you take an even heavier ball, which doesn't jump above the bots, but really sits on the bottom and is caged by the particles and everything, the fluctuation dissipation breaks, and also this relation breaks. I'm not going to show it here, but what we've seen is that when the fluctuation dissipation holds, we can extract in this system that the kinetic and potential temperatures are also the same. In the other system, we saw that the diffusion constant, the diffusive contact works as we expected. I didn't show you because it's work in progress, but there, you could also write fluctuation relations for these systems, especially for the second one. These are work fluctuation relations, and they do hold. So you just have to modify correctly what you mean by effective temperature. And so I guess if you add more particles, if you have a heavier mass, if you do all of these things, then your dissipation processes and fluctuation processes are different. And then you expect everything to break again. So it's only for dilute systems, but I think it's interesting. And with this, I'd like to thank you, the group of the group members that did the work. Dima, Remy is involved in a lot, Mayan in the first part, Galor in the first part, and my collaborator Benjamin, and you.
Questions?
Thank you for a nice talk. And I think that if there are two noises, one is a short noise and random noise, and another one is a collision. It is a little bit, the collision frequency is a little bit larger. In such situation, the non-Gaussian effect should be non-negligible. So I don't think the FDR is held in such situation. So in other words, in your observation that if you are interested in the high frequency regime in the first part, it seems that noise frequencies are almost the same, and everything can be described by Gaussian effect. So the equilibrium counterpart can be expected. Such kind, my observation, is my opinion correct or not?
I would say what you said in a little bit different. I don't think it's the Gaussianity that is important. What I think is important is that all of your noises, whatever they are fast enough. Faster than the thermal relaxation in the system, if you're competing with a bath. So it needs, in some way, it needs to be close enough to white noise. It has to be fast, but it doesn't. But they can be thermal noise is very fast.
Yeah.
The optical forces will never be that fast, but they're fast enough, and that's all they need to be.
Some kind of time scales.
Yes, yes, timescale separation, definitely.
Ma'am, in one of the plot you showed number of hex works versus the temperature. So yes, this one. So in this we see an optimal in number 3.
No. So don't take number 2 seriously. I showed you 2 bugs in the system. It's barely. Yeah, don't take them serious.
Now, I saw that there is some optimal thing at number 3 and not 2.
Yeah, no, I would not. I don't know. I mean, you mean this? You mean this thing?
So why is there optimal at 3 then?
It's okay. First of all, note that within experimental error, this is not a difference.
Okay.
And the other thing is, I don't know, but already in 3, I think I showed the movie.
Yes.
The particle is most of the time, it's a
But
kick and
for
then
2
relax.
also it should do almost the same thing.
Yeah, so I don't know if I can say anything smart about it.
You can't do 3 button problems.
Hello, ma'am. So this bowl has some curvature. Is it affecting the motion, or you take it to make the parabolic this kind of potential? Is it?
Yeah, so this ball is a very funny story. It's actually a plastic ball from a game called, I forgot it now. The toy that spins and they collide. Beyblades. It's a toy that my son had at home. We had a birthday party. I bought several balls for the birthday party. He was 8 at the time. 5 years later, we did the experiment. We needed a ball. I brought them. I think 1 or 2 survived. We dyed them black. We measured their perfect parabolic. Yeah, and they're perfect parabolic to some. Now, 5 years later, they're starting to disintegrate, and you cannot get them because it's always the problem with toys. They want new designs, and the new designs are not parabolic. They're not as big. They're not as. It's really annoying. But yes, it affects the.
Okay. Any other questions?
So in the second part, what you were saying sort of makes a lot of sense to me, that if the fluctuations and if the dissipation is coming from the fluctuations, then fluctuation dissipation theorem holds, of course, if it's but is that in any way related to this other aspect of the high frequency and the faster noise? Like, do you think, like, when those time scales are not separated, again, you have this kind of dissipation coming from other?
Yes, I didn't show the slide. I don't know if I have it. I'm going the wrong way, sorry. Okay, so here you have all the time scales that we have in the styrofoam bowl system. And note that already in 4, okay, so what are the important time scales? There's the relaxation. You're looking at thermal relaxation, which is the relaxation of the styrofoam ball to the bottom. In 3 bots, in the 2 bots, what is controlling this time scale is the time scale of the trap, the gravitation and friction. So you need collisions to be faster than that. And with that, it's similar to what happens other.
If not, thank you again. So we're moving to our last talk of today's. Okay, so the last talk is a short talk by Biswajit Das from ICER, Kolkata, and he'll be telling us about irreversibility of mesoscopic processes with hydrodynamic interactions.
I'm audible, right? Yeah. So first of all, thanks to the organizer for giving us the opportunity to talk about this work. So I would like to talk about our recent work where we looked into the non-equilibrium characteristics in presence of hydrodynamic interaction. So from morning we are hearing many talks, and by now it's clear that if we understand the non-equilibrium characteristics of various system, aspects of interactions are very common. It can start from a simple system, let's say a colloidal particle in a harmonic trap. It's connected to bath with two temperature, so that particle is interacting with bath with two temperature. Or you can construct interaction to know more about such system. Let's say you have an active particle, you want to know about that. Spring can be many kind of interaction. For a generic kind of interaction, what will happen if the strength of the interaction is enhanced? What will happen to the non-equilibrium characteristics? It is generically unknown. Or let's say if you have a system where the noise sources are mutually correlated, giving rise to non-multipartite or co-evolving dynamics. In such situation, the effect of interaction on promoting the non-equilibrium characteristics is typically unknown. So we can think of a simple interaction, that is hydrodynamic interaction, which is nothing but an interaction which couple the dynamics of a two colloidal particles which are close by. So if we consider two colloidal particle, microscopic colloidal particle are trapped close to each other, separated by a distance d, the dynamics of these two particles are coupled by a hydrodynamic interaction. And these are pretty simple interaction, and people have studied the dynamical effect of this, and it is known that even in equilibrium the dynamics of these two particles are anti-correlated at short time. Also it is known if you move one of them, you can get a resonance like behavior in other, you can get synchronization also. Okay. And also there are some works with multiple such particles, some works also told from Professor Yale's group, and many other observations are done with the hydrodynamic interaction. And simply if you consider just two particles connected by hydrodynamic interaction, you can write coupled Langevin dynamics for it. Interestingly, here the deterministic force as well as the stochastic force both are coupled via a hydrodynamic interaction tensor, and which consists of this epsilon, which is the coupling term, which depends on the size of the particle as well as the distance between them, and the noise involved are cross correlated like that. Now in recent times, and this cross correlation is given to a non-multipartite interaction, and in recent times people have started to looking into the non-equilibrium characteristic in such system, and people like Beirut et al, they have looked at like how much heat flow from one particle to another due to such interaction, and they do it like considering trajectory based energetics to individual particle, and they got some apparent violation of LRG balance and things like that. And there are other works even from Reisman's group, people have looked into some other idea how to characterize the irreversibility in terms of phase space, current area and closing rate. So what we wanted to understand is that let's say we have a system with hydrodynamic interaction and a non-equilibrium setup is going on, how the interaction changes the non-equilibrium characteristics in terms of total entropy production rate, and whether we can tune such interaction to get a non-equilibrium steady state of certain entropy production. Also, what will happen if we look into the system from a low dimensional phase space? Let's say we have many degrees of freedom, let's say x1, x2 and a different degree of freedom, and we looked into its effect in a low dimensional only in x1 and x2. What will happen to the entropy production rate? And also we want to reinvestigate this energy balance thing with our entropy production based analysis. To do that, we experimentally design a system where we simply trap two colloidal particles in a finite separation d, and to take the system out of equilibrium, we perturb one of the particle with an Ornstein-Uhlenbeck noise such that your dynamical equation of this whole system can be written in terms of x1, x2 and lambda. And with the hydrodynamic interaction, this system is linear. We can see, we can write down a force matrix and the diffusion matrix with the cross diagonal terms are there. And this system is multivariate Gaussian. So in each marginal will be Gaussian, and we see from experiment the driven particle, which is here is this sky blue color, the variance of that is higher than which one is the fixed particle, and you can see the non-equilibrium current in difference phase. Then we estimate the entropy production rate using with the interaction and with x1, x2, lambda, 3 degree of freedom, and we see the entropy production rate with the interaction is this, and we can take the limit when there is no interaction, we can take epsilon tends to 0. What we get, this without the interaction, the entropy production rate in this phase space, which is spanned by x1, x2 and lambda, is higher than with the interaction. And in experiment we varied this theta. Theta is just basically the strength of the external, theta is in terms of the external noise, and from the experimental data we used this short time inference based key to estimate the entropy production rate, which is just based on this uncertainty relation. By doing the proper optimization, we can get the exact entropy production rate from the from the data as well, from numerical and experimental data. So we see so these lines are analytical and the points are experiment and the open points are numerics. We see for a particular strength of the noise, we see when the interaction strength is lower, we get the higher entropy production, and if the particles are close by when the interaction is higher, we get a lower entropy production rate. And it can be understood in terms of this: when the particles are close by, if the second particle is not there, the first particle with the drive is the current in that space is higher than the particle close by, because the second particle is actually affecting the motion of the first one in presence of hydrodynamic here. Okay, so and also we see by just tuning this interaction, by just placing the particle in different space, we can get a different, we can